Hey everyone, and welcome. Today we're jumping into one of the most important algorithms in all of machine learning, K-means. It's this incredibly powerful tool that lets us find hidden groups in our data. Basically, it turns a total mess into something clear and understandable. It's used for everything from figuring out customer groups to planning where to put warehouses. So yeah, getting a handle on K-means is a really useful skill. So here is the plan for today. First, we're going to talk about the big problem that K-means was built to solve. Then we'll get to know the algorithm itself. After that, we'll break down how it works step by step in what I like to call the centroid dance. We'll cover some pro tips for getting the best results, and finally, we'll look at some really cool real-world examples, both from the past and from right now. Okay, let's kick things off with a fundamental challenge. Just imagine you have a giant pile of data, but you have no labels, no answers. This is the whole world of unsupervised learning. Our job is to find the patterns hidden inside all that chaos, without any hints to guide us. To really get this, just picture it. I give you a file with 1,000,000 scattered data points. That's it, just a cloud of dots. How on earth would you get a computer to automatically sort them into logical groups, like little neighborhoods? It sounds simple, but it's a huge challenge, and it's exactly the problem K-means was born to solve. And that brings us to the formal idea of unsupervised learning. See, with supervised learning, you have neat labels. This picture is a cat, this one is a dog. But here, the algorithm gets nothing. It's like a detective sifting through a mountain of evidence, trying to find connections and patterns without even having a list of suspects. The whole goal is just pure discovery. So, now that we know the problem, let's introduce the hero of our story, the K-means algorithm. It's honestly one of the most popular and just elegant ways to do clustering. People love it because it's so simple and so incredibly efficient at solving this grouping problem. At its core, what K-means is trying to do is pretty simple. It takes your data and tries to split it into a number of groups that you specify. We call that number K. The main goal here is to make sure that the things inside any one group are as similar or as close together as possible. So how does it know if it's doing a good job? Well, it uses this metric called inertia. It's also known as the within cluster sum of squares, which sounds complicated, but the idea is simple. Think of inertia as a measure of how tight the clusters are. For every single point, the algorithm calculates how far it is from the center of its own cluster, squares that distance, and then adds all those squared distances up. The main objective? Get that total number as low as possible. Lower inertia means you've got dense, compact, and well-defined clusters. So how does K-means actually get that inertia number down? It uses this really clever two-step process that repeats over and over, and I love calling it the centroid dance. Okay, the dance begins with step 1, initialize. First, we have to decide on K, the number of clusters we want to find. Then, the algorithm just plops down K random points in our data. We call these points centroids, and they're basically our first guess for where the center of each cluster is. Now, where you place them turns out to be super important, but we'll get back to that in a bit. The next move in the dance is the assignment step. This is pretty straightforward. The algorithm just looks at every single one of your data points and figures out which centroid it's closest to. Then, it assigns that point to that centroid's cluster. Boom! Just like that, you have your first version of the groups. And here comes the magic move, the update step. Now that we have these temporary clusters, the algorithm says, okay, where's the real center of this new group? It looks at all the points in a cluster, calculates their average position, their mean, and then it moves the centroid right to that new spot. And that's the whole dance. It just repeats those two steps, assign, then update, over and over and over again. With every single cycle, those centroids get a little bit closer to the true centers of the natural groups in your data. And eventually, they'll stop moving. The assignments won't change anymore. We call that convergence. It means the dance is over, the clusters are stable, and the algorithm has found its solution. Now, that process sounds pretty simple, right? But to use K-means well, you actually have to make a couple of really important decisions before you even start. And, getting these right is the difference between getting nonsense and getting really insightful results. This brings us to the two giant questions that everyone asks when they first use K-means. Number 1, how in the world do you pick the right number of clusters? How do you know what K should be? And number 2, how do you choose the best starting spots for those centroids so you get a good, reliable result? To find the right k, one of the most popular tricks is called the elbow method. The idea is you run k-means a bunch of times, say for k equals 2, then 3, then 4, and so on. For each run, you plot the inertia. You'll see the inertia always goes down as you add more clusters, but what you're looking for is the elbow on the graph, that spot where the graph starts to flatten out. That point of diminishing returns is usually a really good guess for the best k. Another great tool is silhouette analysis, which basically gives each point a score based on how well it fits in its own cluster versus the next closest one. A higher average score is better. Alright, now for that second big question. Where do we put those starting centroids? This quote really nails it. If you just throw them down randomly, you can get a pretty bad result. You might find clusters that aren't actually the best ones, or even worse, you might get totally different results every single time you run the algorithm, which is a big no-no. So what's the fix? Well, thankfully, there's a much smarter way to start, and it's called k-means++. This is pretty much the standard way to do things now. Instead of being completely random, it's a clever technique that places the initial centroids far away from each other, using the data's distribution as a guide. This one small change makes a massive difference, giving you way better and more consistent clusters. Okay, this is where it all comes together. K-means isn't just some abstract idea from a textbook, it's a real workhorse algorithm that's been solving problems for decades. So let's look at a classic historical example and then a really cool modern one. One of the most famous examples, a real classic, is the iris dataset. This dataset has measurements for 3 different types of iris flowers. And here's the cool part. Researchers fed these measurements into k-means without telling it which flower was which. Just based on the petal and sepal sizes, the algorithm was able to group the flowers into 3 distinct clusters that almost perfectly match the 3 real species. It's just a beautiful old-school example of finding structure in nature. Okay, now let's fast forward to a modern business problem. A textile company in New York had 118 distributors, and they needed to figure out the best spots to build 5 new warehouses. So what do? They used k-means. They clustered their distributors by location, setting k to 5. The algorithm created 5 geographic groups, and the centroids of those clusters gave them the exact optimal coordinates for each new warehouse, saving them a ton of money on delivery costs. But this story doesn't end there. You know, datasets have grown from a few hundred flowers to billions of user interactions, and k-means has evolved right along with them. Today, big platforms like Amazon SageMaker and libraries like scikit-learn often use a version called mini-batch k-means. Instead of looking at all the data on every step of the dance, it just takes small random bites. This makes it so much faster and lets it work on the absolutely massive datasets we have today. So let's just quickly sum things up. The big advantages of k-means: it's simple, it's fast, and it scales really well. But of course, there are trade-offs. The things you have to watch out for are, you have to pick k yourself. It can be sensitive to where you start it, though k-means++ helps a ton. And here's a big one. It kind of assumes your clusters are nice, round, blob-like shapes. And that leads us to a final thought to chew on. We know k-means is fantastic at finding those round, spherical clusters, because that's what a center means. But what happens when the real patterns in your data aren't shaped like that at all? What if you have patterns that look like 2 concentric circles, or long, skinny lines? How would k-means do with those? And what other kinds of tools might you need to find those more complex shapes? That's a great question, and it's really the gateway to the whole wide world of clustering. It's used for everything from figuring out customer groups to planning where to put warehouses. So yeah, getting a handle on k-means is a really useful skill. So here is the plan for today. First, we're going to talk about the big problem that k-means was built to solve. Then we'll get to know the algorithm itself. After that, we'll break down how it works step by step in what I like to call the centroid dance. We'll cover some pro tips for getting the best results, and finally, we'll look at some really cool real-world examples, both from the past and from right now. Okay, let's kick things off with a fundamental challenge. Just imagine you have a giant pile of data, but you have no labels, no answers. This is the whole world of unsupervised learning. Our job is to find the patterns hidden inside all that chaos, without any hints to guide us. To really get this, just picture it. I give you a file with 1 million scattered data points. That's it, just a cloud of dots. How on earth would you get a computer to automatically sort them into logical groups, like little neighborhoods? It sounds simple, but it's a huge challenge, and it's exactly the problem k-means was born to solve.